Thank you. Thanks for having me here. If you're happy with me at the end and you want to invite me again, can we please do it during summer? I'm originally from Florida, so. Anyway, so we're trying to identify the sources of the variable solar wind through advanced image processing techniques. Now, this is work I started with Nikki Weil at Goddard last year, and in collaboration with Hugh Morgan, who was my PhD supervisor in Wales. And so Nikki is very much interested in the solar wind. Hugh is very much image processing guru, and I like to merge the two. So it worked out beautifully when Nikki had this idea for a project. Okay. And that's all I have.
Working a minute ago.
There we go. Oh, okay. Okay. I also just gave this talk at NOAA, so my throat is very dry, so I apologize. Right, so the main motivation is trying to link EUV, or temperature-dependent measurements low in the corona, with coronagraph or density-dependent measurements higher up. Specifically, we're trying to basically close the gap that you see in this image. So here we have a LASCO C2 coronagraph image on the outside, and then the insert is in a 3-wavelength composite of AIA Images. We have this missing link, if you will, between the two data sets. And this is basically a crucial region for understanding the development of transients in the corona. So in a perfect world, we would have a total solar eclipse every day, several times a day. But we don't. So instead, we have this. So the main question is basically what solar structures are contributing to the structures in the heliosphere, aka in situ data. So there has been some success trying to find this link, but it's important to understand the scale at which this link has been made. So there has been some, detection, if you will, of small scale events, small in terms of, compared to the current, the resolution of the imagers, but large compared to turbulence, okay? So we're not talking here about, a full-on structured CME. We're not talking about turbulence. We're talking about whatever it could be that's in between. So let me just put my defense up and say that I have never worked with in situ data, okay? I'm now getting more into it, not just for obvious reasons, because that's what started this whole project, but also because you'll see in a bit how relevant it is to tie together every piece along this map that we're trying to create of the corona, instead of just having this person be this, know this, and this person know that, and then do things indirectly. So I'm going to show you 2-3 examples of how we've made some progress in trying to make this link between the low corona and the high corona, just very briefly, but then I'll come back to example 1 to basically go into what my project is. Okay, so the first example is, so Larry Kepko analyzed, he works a lot, mostly with in situ data, ACE and wind, and so he noticed, can you see the pointer? Okay, in these regions, all these peaks, these are density enhancements. And so he noticed that those, and when Nikki, these right there, when Nikki came along, she focused on analyzing these peaks or these enhancements in terms of basically their own characteristics. So the first thing that came out of that was finding a periodicity. And by that, it means just a characteristic timescale. But later on, she moved on to try and track these density enhancements to try to see where they're coming from. So she actually moved on to remote sensing images, and she was able to track them down through the HI field of view and then into the core 2, which is the image that you see here on the left. So these disturbances that they were seeing in situ, they attributed them to blobs and puffs seen in image data. And I'll come back to it in more detail in a few slides. So the second example that shows some indirect connection that we've made from the low corona to higher up is work that I did on stealth CMEs. So first let me say, we have the term problem storms, but these refer to, the problem refers to the geomagnetic effects of these events. When we talk about stealth CMEs, we're talking about the problem, if you will, being in, where is the origin, or what is the origin in terms of the signature that could be creating the CME, okay? So there have been a few definitions, but the term stealth CME was first coined by Robert et al. In 2009. Did I just hit something? And that's why they're stealth. So. Did I hit something on there?
Good.
Woo! Right. So the main definition is that there is no obvious on-disk signature that could be the source of whatever CME you're seeing further up, mostly in coronagraph data. Okay, so the term stealth CME was coined by Robrecht, but there have been several studies on these CMEs. With a few varied definitions. They don't exhibit low coronal signatures at EUV, or in 2011 may or may not be visible in coronagraph data. That's a slight variation. And then the most recent one before mine was by Elke Das et al. In 2014, and they basically tried to, this is the full definition, the last bullet point that they gave, CME detected in coronagraph images for which no coronal signature observed on disk or in extended field of view. So they were trying to bring out or to extend where they were looking in order to conclude that these events are stealths. So they identified 4 CMEs as stealth CMEs. So here in the box is stealth CMEs, true or false. So my study, what I did is I revisited these 40 events, applying new state-of-the-art image processing techniques, which I will get to. And basically, we found that for each of these 40 events, we did see some form of signature in the general region that could be the source region, that could potentially be creating the CME, okay? Now, in no way were we trying to characterize anything, any physical, analysis, none of that. We were just trying to see if our image techniques could actually bring out such faint events, where, in other data sets, we don't see them, and therefore we have this idea of stealth CMEs, okay? So I'm not saying stealth CMEs don't exist. I'm not saying that they do. I'm just saying this sort of adds a bit to that. So we basically concluded that it could potentially be a limitation on not only instruments, but also on processing. So the third and final example of this linking in situ to the low corona, I just stumbled upon this paper on Monday, and I don't know why I never saw it when I did the stealth work, since it was published in 2013, and I started the stealth work in 2014. And also the first author, her office is 3 doors down from mine, so I took advantage of that and talked to her about it. But basically, it was a CME that was identified as stealth, and she basically traced the evolution of the entire event from in situ data all the way down to the sun. Now, it's a lot more complicated than that. I mean, in 2 hours, we got through the first half of the paper, okay? But it's a very, very elegant paper because she really tries to understand the very scientific name, the 3D-ness of the event, because if you notice in the figure, you have the different viewpoints. You have multi-view imaging, multi-point in situ, you have messenger, you have ACE and wind. So it's a very, very meticulous paper. But, or the positive that comes out of this is that I will be picking her brain a lot, and you'll see why when I get to the details of my project. Okay, so in terms of the image processing, we look mostly at coronagraph and EUV data sets. And so for coronagraphs, Hugh Morgan developed the normalizing radial graded filter, or NRGF, which you may have heard about or have used. And this technique uses a simple filter that basically removes the steep radial gradient. So it reveals the radial structure of the corona. So here in the image, you can see an unprocessed on the left, where you see that, you see that huge drop. Thank you. Yeah. It'll be better for later slides, yes. Okay. That's good, if you guys are good. Yeah. Okay. Just don't fall asleep. Okay, so on the right, this is the process data, so you can see that you're able to extend the signal all the way out to the field of view. But then we have to do something so we can actually see more than just bright lines. So then comes in the dynamic separation technique, or the DST, also developed by Hugh. And this uses a spatial temporal deconvolution-based method, if you're a math person. You can explain that to me later. It separates time series of coronagraph images into quiescent and dynamic components. So it's very effective at revealing the faintest dynamic events. There's no cursor, there we go. These two images, these are LASCO C2 images. So on the left, when you apply the DST, you're left with only the stuff that is moving, okay? So all this, so you're basically subtracting out the quiescent stuff, and you're left with only what's moving, like this and this. If this were a movie, you would see this stuff going out. And then, and this is just an example for Core 2, how it might look. And then in terms of this image, here you have both the quiescent stuff and the transient stuff in the same image. And to get it to this point after the NRGF, we apply the MGN method, which is the next technique, and perhaps the best one. So I'll just let that play for a second. Okay, so which one was the MGN? Okay, I'm just kidding. Okay, so these are AIA images with different techniques. The middle one, yes, is the MGN applied, which I'll explain in the next slide. Okay, I'll kind of explain it here. So when, in any processing, you try to reveal information hidden in EUV images, and we must deal with a wide range of brightness values, preserve the steep spatial gradient in brightness, and respect the fact that, even the brightest regions contain dark patches. Another challenge is, existence of structures at many spatial scales, for example. We can't, and what that means is we can't apply edge detection or enhancement exclusively at small scales, since it will enhance some features, but then we lose others, larger ones. And then with full resolution, with full resolution AIA images, which are about 4,000 plus times 4,000 plus pixels, taken every 11 seconds, we also have to consider computational efficiency. Well, the MGN takes care of all of that, and that's why it's such a good method. And then, seriously, come on. I'll just play it again. And then you get something like this, where you are able to enhance all the detail, the faint stuff without washing out anything due to the brighter stuff. Okay, so I mentioned it in LASCO. So here, yeah, on the left is just the regular after the NRGF, and then on the right you add the MGN so that you're actually seeing the details of the structures that are present in the coronagraph data. And you can apply this technique to EUVI as well. We've applied it to EIT, so any EUV works well. So the best examples of the application of these techniques were obviously the stealth CMEs. So that's why we know they work really well, and the fact that we looked at least 40 events, so it wasn't one isolated things. And there are other studies that came out of these techniques. That's just sort of the best one for illustrating the really faint things. And then you can combine images without losing content. Now in this case, the colors here are just for context. They don't mean anything beyond that. The question, of course, becomes, are the results that we're producing, are they reliable? But it's really less about reliability and more about the purpose of the images that we're using. So with this technique, no artifacts are created, which is great. Any artifacts that may deceive the viewer, they're not created. So such images can be used for reliable estimates of lake structure sizes and velocities. But of course, to gain physical estimates, like density and temperature and things like that, you would turn towards a calibrated image. But for context and sizes and velocities, these work great. And then when all else fails, there's still more. Central median filtering method, it's called. It was developed by Joseph Plowman, and he developed it to track EIT waves. So I've modified it and expanded it to work on EUVI, and I'm hoping it'll work to Core 1, but I'll get to that. So in this event, the stealth event, Robrick's stealth event, they noticed some structure high up in the low corona with the MGM processing. We saw it, but still you couldn't see where it was coming from. So it was too faint for even MGN to pick it up. You couldn't really see it evolved. And next time I show this, I'm going to make a movie instead, because you can actually see there's a small eruption here. You can see a structure forming. Here you see it right there, and then eventually it comes out. So the point here, this isn't adding anything or taking away anything from the Robrick stealth event. This was just me testing this method and how we are still able to work with data and the parameters in these techniques and so on to bring out the structures that we want. Okay, so with that, I am focusing on applying these techniques to try and find the sources of the slow solar wind. So one question I got at NOAA this morning after my talk is, why focus on such little structures? I was talking to a room full of space weather forecasters, and yeah. But the thing is, we're trying to find the sources of the slow solar wind. Okay, we've noticed these density enhancements. Forget about the periodicity. Okay, I've heard different views on that. But the fact that there are density enhancements, the fact that we see them initially, if you know about Scheele blobs, these blobs that generate at the cusp of helmet streamers and feed into the slow solar wind. But with the in situ data that Nikki has seen, she has seen them in pseudo-streamers indirectly. Now with some of Craig DeForest's processing, it looks like they found them. We don't have enough to publish, but we think they're there. The point is, I guess one of the many points is, we understand the fast solar wind. ish, what is feeding into the slow solar wind and causing these density enhancements that we're seeing, okay? So that's where I come in. And so the events that she looked at a 10-day period in 2008. 2008 was a quiet period for the sun, okay? So from in situ, we know that these enhancements, they are the slow solar wind, okay? So presumably whatever we see in EUV data, whatever we see low in the corona should be what's creating the slow solar wind. So that's why I started focusing on that time period. But eventually we're going to expand to other time periods, more magnetically complex ones. Okay. Okay, so we hope to answer questions like these. Basically, at what heights do slow wind structures form? Which features in the low corona do they connect to? And any variability that we may find. How much of what we're seeing low in the corona is the same that Nikki saw high up in the corona and in situ? Okay. So this is pretty much the magnetic configuration in 2008, January 2008. Okay. So where are these events mapping to? Okay, so I said that the periodicity, that's a characteristic timescale. So as Nikki traced these events further down into the corona, every time she saw them in a field of view closer to the sun, they were already formed in that field of view. So it stands to reason that they were coming from lower, right? From a lower portion. So eventually, I just put them up because this is the actual in situ data for these 10-day events. But she started in HI1. There was some kind of differencing that she did. These are the density enhancements, more or less, that she identified, and eventually made it down to core 2. Okay? So after I applied these techniques to the data that we currently have, the data that I have worked or that I had worked with up until when I started this project, is EUVI and core 2. So at the top left is the movie from Nikki's work. That's a composite of HI, EUVI, core 2 and EUVI. And now I'll play my movies with my processing techniques. So in 171, that's where you see more. You should see a structure here. Did you miss it? No, there it goes. Do you see it? It's very faint.
I saw it.
Okay, thank you. Okay, so
can you tell us where those arrows are relative to the current sheet? In other words, are we looking at the locations of where the current sheet would be in the low solar line?
So that's the thing. So if we go to the extrapolation that I showed, this one. The thing is that in the movies we're seeing some structure in a number of places, right? So the problem now is identifying where these are in relation to, for example, a streamer, and are they actually contributing? Which one is contributing to what? So basically I'm saying I don't know. So in 304 for EUVI you can't really see anything. But in the 171 you see that eruption at the top there. Now it does seem to take this shape here, doesn't it? Or am I just reaching? Like I'm genuinely asking you.
Look at it for a long time.
I know. That's and believe me, I have. So I really don't know. Oh, man. Okay. So just for kicks, I looked at LASCO. Because the stereo A and B were in this position, so LASCO could capture something a couple of days before in the almost the same region, or same region. So you do see blobs and such. But of course, what EUV data can you look at if you're looking at LASCO? It's EIT. The problem with EIT, aside from the resolution, is that we're missing a lot of files. There's a lot of data gaps. So that doesn't help either. Yeah. Okay, so how can we proceed? Maybe look at wider fields of view, right? So we have SWAP, which has a 1.67 solar radii field of view. But then the data is only available since 2010. So for these particular events, that's no help. SUVI data has been available since last year, maybe a few months before. Before that, and the field of view is great. It's 2.5 in the corners. And we know the processing techniques, work because here this is SWAP at the bottom. So this is their processed image. This is my processed image. This is SUVI, that's theirs. This is mine. So we can bring out all these events. We'll have to work a little bit more about, extending these features, although you couldn't track them. Anyway, details. But, and the large field of view. But this data is not available, except after just a few years ago. And SUVI just last year. Okay, so obviously Core 1 is on our mind since these first events were in the stereo suit. So I always forget that this movie runs way too long. So so in Core 1, these images you may have seen, this is how the data stands online. If I just move, that's not moving, hang on. Looking here on the east limb, you see right there, let me go back. Right there, yeah? Do you see that? Okay, there's something there. It matches in general region. Do we know what it is? It could be that event that we saw in the 171. If you play these movies, they match in time. Maybe even in how they sort of restructure that streamer. But we can't be sure. And we're talking about 10 days. That Core 1 movie is 10 days. We only see that one thing because we need to be able to bring out more of these details, okay? The NRGF method we've tried with for this event. The NRGF is really good with, for example, EUV image, where you can basically match up the different fields of view. But again, it only works for larger structures. So we're still at a loss. So back to the center median filtering. The thing about this method is that you can change the window that is used in the code to basically get a median to subtract, with a couple of steps in there. So you can you make the window larger if you're trying to capture something slower, something fainter, and so on. So it's great. But it works really well when we have a cadence much like AIA, right? Where we're talking about seconds. So as you increase the window, then you start to see more of these structures like this one here and so on. Okay, so we're looking at very faint structures. Some of these methods work better with, you need the resolution, you need the cadence, and also if we're looking at these, for example, how do we know these structures are not a result of, it's not a result of the processing, we've established that, and let's all pretend like we believe that. it could be a result of, you have the rotation, especially since they're so close to the pole or whatever. We're not sure. I hope you're getting the theme by now that this is a very open-ended project. So then there are other methods we can try. Jones and Davila managed to basically confirm density enhancements low in the core 1 that could be these blobs that we see, these periodic density structures. One thing I should point out, I don't know if I said this already, the Scheele blobs, they form in helmet streamers, but we're talking about pseudo streamers, which is what has been observed, but not quite in the imaging data, okay? So this is something else to try because Shayla Jones, she only did it for one particular event, okay? So I have her codes and we'll see what we do with that. So the question is still, what are we seeing? We are seeing stuff. The techniques have helped to reveal things, but the problem is now not only the problem that we've had from the beginning, actually connecting it, but actually interpreting it. So then you look at something like, there were no CMEs except for one CME at the end of this 10-day period, like the day after or something. In terms of what's going on in magnetograms, well, as you can see, not much. So one thought for the future is to look for similar events in, for example, this is just an example, 2011 because of the position of stereo, and then we have, we could throw in LASCO here, and we basically get a whole view of the sun. Okay, so that's one thought. We can look at more magnetically complex time periods, like to include, or looking at pseudostreamers, but like active regions or different periods along the solar cycle. Is there any correlation between these density structures and the solar cycle? Do they fluctuate during the cycle? Are they steady? Okay, and we can look for 2008, there's MK4. I was just talking to some of you about this. And or K-core, because we have that wider field of view. So hopefully I can start working with some of that data. So the problem is, well, one of the many problems is that we started all these events, the stealths, the periodic density structures. We started with something we already saw, right? And we're tracing it back. But now we have to expand it because we can't just say, these are the sources of the solar wind, assuming we got to that point, which we haven't. But the problem is in moving to other time periods, we have nothing to compare it to. Okay, so what are we looking for? Do we just keep staring at movies and finding these very faint structures? But what do they mean? And is there something predictive enough in those results that could tell us something about the measurements that we're seeing further out, or anything in terms of space weather forecasting and things like that? So the argument is made, how much do we care about these small structures? Okay, in terms of space weather. But again, we're looking at the slow solar wind. So some of these things obviously make it out to at least 1 AU. So something is happening, okay? So this project has been and continues to be very much an open-ended project. Since we don't know exactly what we're looking for, we are open to explore everything and anything we can in terms of data and processing methods and so on. However, it then becomes difficult to decide where to take all that information we have thus far. So there are plenty of ideas, which I tried to outline, but I very much welcome your suggestions. So thank you.
All right, plenty of time for questions, if I can see people sticking up their hands. Was that you, Ricky?
That was Lefter Below.
Oh, I see. Joan?
There's a paper, I forget when it was published, 10 or 15 years ago. It's Eric Andy, Tom Holzer. He was running a model of the stability of these above the helmet stream or where the current sheet is.
Mm-hmm.
And he does find periodic reconnections at the boundary and the stalk. And so you
Okay.
can look at that in terms of, I'm not saying that's the final solution
Right,
that
right.
you're looking for.
And then I
But
can-
I'm saying here's a model that's showing you that periodic reconnection occurs at the boundary. So you can take a look at that.
What was the name again? I'm sorry.
Eric Endivie. I have to
Oh,
look it up.
yeah, I've seen the name, yes.
Yeah, and Tom Holder's on there too, and Eric Egelleer.
Okay.
And since I'm old, I think it's 10 years, it was probably 20 years ago. But it seemed like yesterday. But I can help you track down it because it's directly related to these blobs that you're talking about. in terms of
Thank you.
Periodic reconnection of the current sheet.
Okay. Thank you.
More questions?
I wonder if some combination of triangulation with stereo plus things like things like PFSS models. I wonder if those would be useful in figuring out where things come from.
Yeah, I think so, and I think especially when we move on to the more complex dates, like I said, maybe 2011, where we have the multi-view. Yeah. Yes. Thank you.
Anyone else?
A question that I don't know how to phrase.
Okay.
I'm not sure what question it is. But I've seen a couple times talks by Craig DeForest on image reconstruction of this kind of like spread imager images and so on. Have you looked at those work? How do your methods fit with his?
Well, mine are better. No, I'm just kidding. No, I'm glad you said that because I did want to point this out. I do have a meeting with him tomorrow, so I will gang up on him on my way to the airport. So his technique, if we talk about the dirty math, is a slightly different way of analyzing than Hughes and mine. But he does a lot of like deep field, further out type thing. But the blobs, the Scheele blobs, have been seen in helmet streamers in image data, but in pseudo streamers they have not been seen in image data. But Nikki did take a look at Craig's process stuff recently, and she did see a few. So there is a possibility, and I will talk to him about that tomorrow. Yeah. Thanks. By the way, these the NRGF gets used for the K-core, but the other codes, they're technically publicly available, but they're really not. So part of what I'll be doing the 2 weeks that I'll be in Wales next week, I leave next week, is to basically, we have these codes, but I've changed them, I've improved them, so has Hugh. We're basically going to merge them. I've also been working on getting these codes, because first it was like one code for EUV data. It's not that black and white, okay? So I've been working to basically modify it depending on which data set, which wavelength, things like that, okay? And so we're basically gonna create a very, very user-friendly set of codes, and we're going to share them on GitHub. And while I'm up here, I just got word today that a session I proposed for Shine got accepted. And it's basically on image processing, but also on tools, on data analysis tools. And this is all in preparation for the instruments on DKIST, Parker, and Orbiter. Okay, so basically to understand what we have now, how we can use it, how we use it, and how we can modify it for those future instruments. Okay, so just FYI. Yeah.
Any more questions, comments? If not, let's thank Nathalia again.